Hello, everyone. A very good evening to you all. This is Balaji Srinivasan, your instructor for Introduction to Photonics course. So it's been a very uh, uncertain time, a difficult time, challenging time for all of us, I suppose, this past month or so. And it still remains to be seen how much longer we'll have to go down this road. But we will do what we can in these circumstances, think positive and try to get on with all our education related activities. So it's been a very productive time for me personally because I've been able to go online and get in touch with a lot of students, research scholars, collaborators, and still be able to do some significant work. So we'd love to thank the internet for all of that. And of course, from your perspective, learning in these circumstances is quite challenging. And so I'm sure you have your own set of issues which I may not be completely able to comprehend. Nevertheless, we come to a point in the course where all the lectures are done, all the assignments are done, and there have been a few hiccups along the way, a couple of errors in the lectures that were promptly pointed out by the learners, and that's been quite helpful. And there have been some issues with the assignments also, which we have tried to take care of. And hopefully we're all in good space right now with whatever has gone on. If you still have issues, please do bring it up as soon as possible so that we can try to get that corrected. Well, this live session I thought we could use for a couple of purposes. One is to sort of project what's going to happen from here on. And two, to answer some of the questions that you have raised or some of the questions that you may have at this point. So first of all, with respect to what is going to happen from here on, we still are quite uncertain about when that final exam is going to happen. I'm told that everybody is waiting to see how things develop after the lockdown period gets over, May 4th, and then we'll go from there. But as of now, the final exam is sort of postponed indefinitely. So what we can do in this period while we are waiting for the final exam to happen is to test our knowledge against some sample question papers. So this is what I'm planning to do. I will probably give you a couple of sample papers that you could potentially try to work out, and we can discuss the solutions and all that. And I'm also trying to see whether NPTEL can arrange for you to go back and sample some of the assignment questions, and even though the evaluation is closed, maybe you could be allowed to answer some of those questions as well. So that could help you in your preparations whenever the final exam is going to happen. So that's where we stand as far as our plans further are concerned. But in the meantime, if you have any other suggestions or any queries related to this, you may please put that up in the discussion board, and we'll try to address that. So with that sort of a background, let me go on to addressing some of the questions that you have already raised. Thank you for several of you that have raised these questions. So just give me a minute to pull up those questions in front of me. So this is actually a different sort of interface than what I'm typically used to. So pardon me if things look a little choppy or I'm not being very coherent with my actions. So let's just go through the questions one by one. And at the outset, I will tell you that there are some questions which are about material that's beyond what we have covered as far as this course is concerned. And then there are also some questions that I see which are too specific, specific numbers and all that with respect to an assignment. Unfortunately, I'm not prepared to answer those because I don't have all the exact numbers in front of me. But I will try to just see how well I could address those questions. So let's start with this first set of questions. It's about doing research related to a fiber Bragg grating based sensor. So clearly, this is a question that is uh, beyond what we have taught in the course, but nevertheless, I can spend a couple of minutes, maybe try to answer this. Uh, the person is asked, describe about the cross sensitivity in FBG sensors and how do we deal with it. So for that, maybe I can just use my right pad here and explain how this is working. So hopefully you can see my right pad now. So we're talking about fiber Bragg. Okay, start streaming. Uh, Hello, guys. Uh, so sorry about this trouble. I suppose there's some infrastructure issues, maybe network, and maybe this writing pad is also not cooperating. So uh, given all that, I think what we'll do is I also see messages from you saying that whatever I'm speaking, you're not able to hear properly. So given all this, let me just not go to writing mode. Let me just stay with you on this video and try to answer your questions as much as possible. So I'm going to have to do a lot of hand waving just to get my thoughts across, but hopefully, that you can still understand what I'm talking about. Okay, so let me just go back to the list of questions we were looking at and try to answer those. So the next question is about distributed sensing. Question is about Raman or Bruon fiber-based sensing of temperature and strain. Uh, how it can be used for the ocean environment. And so first of all, I think during the lectures I was talking about the fact that you can combine this scattering principles, inelastic scattering principles like Raman or Bruon scattering uh, into you can basically observe that in a fiber environment. You can combine this with what is called optical time domain reflectometry to get a distributed strain or temperature information. So typically, Raman scattering, as I mentioned in the lectures, is used for distributed temperature sensing, and Bruin scattering can be used for both strain as well as temperature. Um, so the question is which one of these can be used for a harsh environment like an ocean, and I don't want to go into the details of that, but if you can actually put a fiber in the ocean, um, you can certainly observe these physical parameters. The biggest challenge that's going to be when you do this is whether the fiber, the way it's packaged so that it can remain in the ocean for long periods of time, whether that package would allow the strain or temperature, a true measurement of strain or temperature in the external environment. That actually is the biggest challenge. So it all comes down to how well you can package the fiber. But if you manage to package the fiber, then there should not be any issue in measuring, like I said, temperature using Raman or strain using Bruin scattering in the optical fiber. Uh, the other question is sensitivity and performance uh, good for FBG or such scattering based uh, fiber optic sensors? So the question is about whether we should use distributed Raman or Bruin scattering based sensors or fiber Bragg ratings, and it really depends on the application, but all said and done, fiber Bragg ratings are point sensors, so they allow you to measure strain or temperature only at a particular point, whereas these other distributed sensors based on Raman or Bruin allows you to make measurements along the fiber, entire length of the fiber. So those are two different classes. So in terms of sensitivity, um, yeah, fiber Bragg ratings are fairly sensitive to strain and temperature. They can give you a relatively easier way of measuring strain or temperature. But I think the key point is FBG is a point sensor, whereas the other scattering based sensors are distributed sensors. And another question is about how these scattering based sensors work when they are subjected to high energy radiation like gamma ray exposures. Once again, this is not something that we discuss as part of the course. But what I can tell you is when you have high energy radiation falling on this optical fiber, basically made out of fused silica, they end up breaking bonds because their energy is greater than the bond energy in the glass. So they end up breaking up bonds in the fiber. So they change the composition, or rather they change the structure of the optical fiber itself, and that in turn results in a large absorption that takes place, or the large loss that happens within the fiber. So, and the loss tends to be more for shorter wavelengths than longer wavelengths. In other words, longer wavelengths are the scattering is more for the shorter wavelengths, and it's not as much scattering in longer wavelengths. So if you are using, say, near infrared radiation beyond 1 micron wavelength or maybe even 2 micron wavelength, you may not actually have as much loss in the fiber as you would have for shorter wavelengths. So hopefully that gives you some idea about how these fibers can be used in an environment which has high energy radiation. And then there is a question about using multimode fibers uh, which are actually having a certain bend radius. How can we simulate the output power and also simulate the mode field? Now, I think at multimode fibers, we talked about this maybe in the second week of classes, where we said you can actually analyze them with the array model itself. And one of the things we talked about there is when you bend the optical fiber, it changes the total internal condition for some of the higher order modes. So that results in higher loss for higher order modes compared to the lower order mode, the fundamental modes. So based on that sort of a theory, you can probably project what you will see at the output. So I'm not giving you a direct answer, but that is something, some specific analysis you need to do to figure out what is the output that's coming for a given bend radius. Like I said, if I had my writing pad, I would have probably tried to draw the picture and show that to you, but unfortunately, that's not happening today. Then there is a question about a couple of assignment solutions. Unfortunately, these are going too much into detail that I don't have the assignments in front of me, so I cannot actually give you the answer for this. But if you can actually put up the same question out in a discussion forum, I'm sure we can take a look at it and give you the answer. Then we'll move on to the next question, which is about an EDFA. How will the EDFA affect the amplified laser line width if the laser has a very narrow line width? That's a very good question. So clearly, if your laser has a very narrow line width and you send it through the EDFA, the photons within that spectral band of the laser, they will stimulate uh, these transitions within the EDFA if the wavelengths around 1550 nanometers. So you will see amplification of those of that radiation. However, as we know in a EDFA, whenever you pump uh, these erbium ions to the higher energy level, you cannot guarantee that all of the ions are going to be stimulated. So some of the ions can also cause spontaneous emission, um, and especially when conditions where there are very few photons coming into the fiber to stimulate these transitions. You may have a lot of spontaneous emission in that case. And in that scenario, the spontaneous emission can get amplified as it propagates down the EDFA. And so you have what is called amplified spontaneous emission. So at the output of the EDFA, you will see a amplified version of the narrow line of the incoming laser, and you should also have some what do you call wings, some extra spectral features corresponding to the amplified spontaneous emission noise. So that is something that you have to be very careful about when you are trying to amplify a narrow line with laser, right? The next question is about is is there a commercial optical cable transition between multimode fiber to single mode fiber using a taper approach to minimize the optical losses? This is again a very good conceptual question. And to answer this, I would have to take your attention back to the electromagnetic optics that we discussed in the third week of our lectures. We talked about how we have modes in an optical fiber. right? And we talked about how a single mode fiber carries only the fundamental mode, and the fundamental mode is a electromagnetic field configuration that propagates almost straight down the axis of the waveguide. Now, when you have a multimode fiber, you have multiple modes which correspond to multiple wave vectors uh, that are not only along the axis of the fiber but also at different angles with respect to the axis of the fiber. So when you try to couple a multimode fiber output into a single mode fiber, what you will see is that only one um, mode is getting coupled. One of the multiple modes is getting coupled into the single mode fiber, and so you will have a huge loss at that point. So even when you use a tapered approach, the taper will essentially end up only what do you call filtering out the higher order modes. It will not convert the higher order modes to the fundamental mode. If you want to do that sort of a conversion, you have to use, this is actually a research problem that we are working on right now. We are making a sensor for this COVID virus detection, and that sensor cartridge needs to essentially couple light from a multimode fiber into a single mode fiber. So in that case, we are actually using some conversion devices called long period gratings. If you are interested, you can write to me and then I can explain to you how that grating works. But normally, if you connect a multimode fiber to a single mode fiber, only one of the multiple modes will get coupled into the single mode fiber. So you will have a huge loss at that point, and it's not easy to get around that loss. Hopefully that answers the question. Then there is a question about how does reflections from the output disrupt the amplifier operation? What is done to prevent it? So this is once again a very good conceptual question. So how the reflections disrupt the amplifier operation, you can probably understand by looking at what happens in a laser. So what is the difference between an amplifier and a laser? Well, a laser is nothing but an amplifier with feedback, right? So that feedback essentially stimulates further transitions, and then you have the concept of gain versus loss, which results in the laser oscillation. So that is the key point that you want to think about when you have reflections from the output side of the amplifier. Those reflections can essentially cause laser oscillations in the amplifier. And what's bad about it is the laser oscillation, as we looked into when we were discussing lasers, the laser oscillation can happen at any wavelength that's decided by the gain versus loss, the net gain that we are seeing, and then the saturation issues in the laser cavity. So that wavelength may not be the wavelength that you're trying to amplify. So for example, you may come in with 1540 nanometer radiation, you want to amplify that, but because of reflections, this laser oscillation may happen at 1550 nanometers. And in the case of say telecommunications, you are trying to amplify some data at 1540 nanometers, but you have some laser oscillation happening at 1550 nanometers, which has nothing to do with the data that you're trying to transmit. So that is absolutely not a desirable thing when you're using these amplifiers for such applications. So how do you prevent it? Well, you can prevent it by putting an isolator, and this is what we talked about, some 2-3 weeks ago when we were looking at polarization-based optical components. We talked about Faraday rotators, and using a Faraday rotator, how to make an isolator, and also we talked about how to make a polarization insensitive isolator, or how to make a circulator also. So uh, essentially, if you put an isolator at the output of the amplifier, this is something that is explained also in the lab video during the week when we were teaching amplifiers. If you go back and look at that video, you will see that we use an amplifier in that case to prevent reflections from the output. Okay, hopefully that is answering this question. And then there are some questions once again about stimulated Bruin and Raman scattering, that we have not actually given the threshold value at which stimulated and Raman scattering happens. True, those are some advanced concepts that we did not want to get into as far as this course is concerned. But now that you asked the question, let me just try to answer that. Let's just take an example of an optical fiber, a single mode optical fiber that's typically used for telecommunication. So if you consider a single mode optical fiber, if you have a length, let's say in telecommunications, you typically have lengths of 10 kilometers or higher. If you have that sort of length, stimulated Bruin scattering sets in about 7-8 milliwatts, roughly about 10 milliwatts of power. Okay, so you're not going to be able to transmit more than 10 milliwatts of power with a narrow line with source, uh, uh, you know, when you have long lengths of fiber. So that's sort of the threshold. But note that this threshold condition depends on multiple factors. It depends on the medium that you are propagating. In this case, is an optical fiber. The length of the medium that we are propagating it through, and also the line width is a very important thing. So we talked about Bruin scattering. We assumed a monochromatic light source that's coming into the optical fiber, and because only a monochromatic light source can give you a strong standing wave pattern, a strong grating, which supports a lot of scattering, right? So, so in certain ways, if you want to um, not have stimulated Bruin scattering happening, the best way to do that is to chirp the laser. Chirp the laser meaning you make the line width of the laser, if it is so narrow, if you make it broad, then that is actually a very effective strategy um, to push out the threshold of stimulated Bruin scattering, and you can go to even higher power levels. And in fact, that is the technique that we use in our high power fiber lasers, where fiber amplifiers, where stimulated Bruin scattering is actually a limitation. So we try to get around the limitation by essentially chirping the line width of our laser source. Now, similarly, Raman scattering once again depends on the length of the fiber that we're using, the Raman scattering coefficient of the material. So, if you're using silica fibers, for example, um, if you assume you have, say, once again 10 kilometers of fiber, stimulated Raman scattering, you may start observing at about close to a watt power level. So that is sort of the threshold value that you have there. But like I said, to really quantify this properly, you need to rigorously solve the rate equations that I projected during our lectures, and you need to solve them simultaneously to get the actual threshold values. So can you take up one more session to explain the recent advancements and applications about this field? I wish I could, or maybe I'm actually giving a talk to a company on Tuesday next week, a company that we are collaborating with, and I know that talk is going to be recorded. So if they would allow access to that recording, I can put that up, and there I do expect that I'll be talking about some of these issues. So I can make that available to you. And lastly, the question is, please explain the EDFA in detail. Sorry, I'm not going to do that right now. First of all, I don't have anything to write on, but I suppose there is enough information available through the lectures. You can go back and view the lectures, and if you have very specific questions, if you can write to me, I'll be more than happy to answer those. Okay, so then we move on to the next question, which is, apart from optical pumping, can any other pumping mechanism such as electrical be used for fiber lasers? So that's an interesting thought. Yes, all we need to achieve population inversion as far as a fiber amplifier is concerned is to excite these ions to a higher energy level. And we typically talked about optical pumping, although with semiconductor amplifiers and light sources, we talked about electrical pumping there. But as for coming back to a fiber, it is not easy to do electrical pumping because you're essentially looking at a dielectric medium, so you're not going to be able to uh, essentially supply that sort of energy so that it can go to the higher energy level. So the short answer to the question is electrical pumping is not going to be possible for a fiber laser just because of the nature of the medium that we are looking at. But clearly in semiconductor lasers, that's what we do. We use electrical pumping. This is actually a name that I don't recognize from our course, Juan Sojo. Anyway, the question is about nonlinear Schrodinger wave equation, and I would say that this is it's basically an extension of the wave equation, but nevertheless, we won't go into that. That is something that you may read about if you take a course in nonlinear optics, a proper course in nonlinear optics, so which is beyond the scope of this particular course. Okay, so that's all the questions I got through the form. So let me just see if there are any other questions that we have. Okay, there have been a lot of complaints about my microphone not being in position. Sorry, I'm just seeing some of your messages, so I was not able to address that earlier. But let me see if there are any other questions. Nope. So all I see is comments about the quality of the network and the difficulties that you are having in following what I've been talking about. Uh, I'm really sorry about that, but on the other hand, this is not an ideal situation. so we did not anticipate having to, for me to sit at home and communicate to you through my laptop and all that with the limited infrastructure that I have. So, given all that, I hope you understand. We're just trying to do the best we can, but sometimes that best is not good enough. So, with that, I think we come to the end of this particular session. And I do see a suggestion for maybe one more session. Yes, why not? If you don't mind the issues that we are having with bandwidth and all that, I don't mind. I mean, I can keep meeting you like this every Friday evening if you like. But please keep that feedback coming. So as long as you guys can come up with questions, I'm here to answer them. At least until we get to the final exam. Uh, so there is, well, one last question about sensitivity matrix. I think that is something I'll have to take offline. Anyway, I don't have anything to write on so right now, so I'll leave it at that. So with that, I wish you the very best. Hopefully, you guys can stay safe with your respective families, and we can get through this situation as quickly as possible. But on the other hand, I do encourage you to use this opportunity to learn the subject in a little more deeper manner, and I'm around to help you in that. So please go ahead and keep asking questions. I'll be more than happy to answer those questions in our discussion forum. Okay, thank you all. Bye now.